Fantastic. Is that better? Okay. All right, yes, so hello everyone. My name is Joseph Dolphin. I'm a second year PhD student at the University of Cambridge, but I do all of my research at the Toshiba Quantum Information Laboratory. I'm part of a team headed up by Taufik Parezo that's interested in the application of integrated photonics to QKD. And so today I'm going to be talking about an effort to apply hybrid photonic integration to QKD, which I'm very grateful for the opportunity to present. So I've had a fantastic lead-in from the previous talk on my topic. There's been a recognition for some time that integrated photonics offers an opportunity for a more scalable implementation of QKD systems. And it's a really exciting time at the moment because whilst it has its kind of inherent advantages, it's been historically playing catch up with the discrete optics systems. But over about the past year, we've seen the on-chip QKD systems just match or blast past the discrete optics systems. But when designing QKD chips, the very first decision you have to make is what material platform am I going to make it out of? And unlike in integrated electronics, where there's one material that does 99% of what you need it to do, like silicon, we don't have that in integrated photonics. And so the design of QKD chips, whether it's both the transmitter and the receiver, is constrained by the properties of the material platforms that we have available. But this challenge has actually been overcome by classical integrated photonics. And the answer has been hybrid integration, where you bring together two material platforms together into one structure, and then you can specialize different parts of your circuits to get the best properties available. And we think there's been a kind of assumption that this is either too lossy for quantum technologies, or maybe that it's not quite mature enough yet. But it could allow you to do things that, while the monolithic chips are doing a really good job, it can allow you to do things that maybe they can't quite do. And we wanted to challenge this kind of paradigm. So when I talk about hybrid integration, I'm talking about lots of different techniques where you're bringing multiple material platforms together. And in this work, where we were interested in creating a QKD transceiver, what we went for is edge coupling. So this one on the top left. So it's pretty straightforward. You get two monolithic chips and you bring them together with structures on the side to improve the coupling, and you permanently bond them together. And the reason we went for this is twofold. So firstly, it gives some of the lowest optical losses of hybrid integration, which really matters for us when we're doing QKD. And secondly, it's a mature technology that you can get done commercially now. So we can actually get this done, at least on small scale, right now. So what does our chip look like? Well, what we made was a hybrid indium phosphide silicon nitride QKD transceiver PIC. So we have on the left an indium phosphide section that gives us two electro-optic phase modulators. They have a nice high bandwidth, low V-pi, and a nice constant loss, so no kind of phase-dependent loss going on there. And then on the right-hand side, you've got a silicon nitride chip. And silicon nitride gives you a nice low propagation loss, it's precise manufacturing, and it has integrated thermo-optic phase shifters, so you can tune the behavior of the structure at slow frequencies. So those two chips were brought together, permanently bonded with index matching gel. We have structures in there to help with that alignment process. And we made a number of these chips, and we were able to characterize what the typical loss was. And we achieve a sub dB loss on this interface here. And then for this, these chips are meant to operate as a transceiver. So they do both the encoding in one half and the decoding in the other at 1 gigahertz. And the total loss from fiber to fiber going into these chips was typically about 7.5 dB. So exactly how does this work? Well, similarly to the previous talk, we're operating on a time bin encoding QKD, which is slightly different. So if you imagine the block sphere, if you've got the early and the late time bin, and they form your polar states of the block sphere, then we're using the equatorial states. So all of our qubits have an equal intensity of early and late, and we're simply changing the phase that we apply to the relative phase between the early and the late time bin. So let's say you're operating the encoder circuit, and that's the top circuit. Then what you need to have is an external laser input running at 1 gigahertz. That goes into the silicon nitride interferometer structure. So that's going to split your 1 gigahertz pulse into 2 early and late time bin of equal intensity. It's then going to proceed onto the transmitting EOPM that's going to apply a phase shift only to the early pulse. And thus, depending on what voltage you apply to it, 1 of 4 levels, you're going to put your qubits into 1 of 4 time bin phase encoded states. Then the pulses will proceed out and go on to whoever's going to receive them. And then if you're acting as a decoder, then you get those qubits coming in from the transmitter, they come through and they first proceed to a receiving EOPM. And that's also, yet again, just going to apply a phase shift to the early time bin pulse. It's going to apply either a 0 or pi by 2, which corresponds to either putting you in the X majority basis or the Y basis. So we can measure 2 orthogonal measurement bases actively modulated. So we wanted to characterize how this works. So we took 2 of our hybrid transceiver picks and we set them facing each other across a duplex fiber channel. So each hybrid pick has an externally modulated laser chip. This is actually indium phosphide, exactly the same as the modulator platform is. And it has a laser on it, and it also has an intensity modulator, so it can apply a 3-level decoy state implementation to protect against photon number splitting attacks. That feeds into the encoding side. And then on the decoding side, you've got 2 SNSPDs, and they're just kind of run-of-the-mill, 85% detection efficiency, about 100 dark counts per second SNSPDs, so no fancy multi-pixel SNSPDs, unfortunately. And I've provided in the bottom left a little bit of a less kind of stylized schematic of what's going on that also includes the electronics that we used. And what we're not doing currently is we haven't got the kind of real-time processing electronics that you saw in the previous talk. So we haven't got kind of FPGAs and stuff crunching through the qubits in real time. We just have to send a repeating, in this case, 10,000 nanosecond pseudo-random pattern on some AWGs that then do the actual control of the EOPMs. And then detection events come off the SNSPDs, and then the secure key rate is estimated in post-processing afterwards. And we do that either in an asymptotic regime or a finite key regime, depending on what's most appropriate for the data we've taken. So what performance do we get? Well, we can replace, instead of having fiber spools here, we can have a VOA, a variable optical attenuator, and we can step through in 3 dB increments and see how the system behaves. So you've got here the raw bit rate in orange, you've got the qubit in blue here, and you've got the estimated secure key rate here. And we can see that we can kind of push past about 40 dB, and we have kind of sub 1% qubit in both bases combined. And we're really pleased with this because it's done in the phase encoding, which is actually quite difficult to do. And it's really down to the fact that we have the combination of the indium phosphide and the silicon nitride. The indium phosphide modulators are really accurate, and the silicon nitride interferometer structure is precisely manufactured, and you can do all that fine tuning with the thermo-optic phase shifters. Our kind of detectors saturated at kind of a 7 dB channel point, so that's the lowest we could go. But at 7 dB, we can get about 1.5 megabits per second of secure key rate. But of course, we have their transceivers, and they're facing each other over a duplex channel. So we can do simultaneously in the opposite direction. And so we can see that we get basically the same performance going the other way. So we can have about over a megabit per second of secure key exchange simultaneously and bidirectionally between these transceivers. And we're kind of, this is useful, I guess, in the sense that you just double your key rate straightforwardly. But I think we're most excited in terms of the applications in terms of making networks. So we imagine it's going to be quite awkward to have, for want of a better word, kind of gendered nodes. And the fact that if you can have each one as a transceiver, it can then flexibly form ring networks and line networks, which we're quite excited about. But of course, this is just over an emulated loss link. So we can try doing over real fiber spools, which are these stars that have just popped up here. This requires fiber stabilization stuff. So you've got the drifting polarization, silicon nitride is polarization sensitive, and you've got the drifting timing. But once you take those things into account with stabilization algorithms, then we can kind of match the performance that we just get on the emulated loss links. We wanted to see how far we could push this in terms of distance in this hybrid chip. And unfortunately, what we found we needed to do was cut off one of the transmission channels. And that was because we started to encounter problems we didn't really anticipate, which was crosstalk between our two channels of our transceiver PIC. So you have a little bit of electrical crosstalk in the phase modulators, but it only corresponds to about 0.1% of Cuba. But more importantly, you've actually got optical crosstalk. So somewhere in our chip, we have leakage of light from the transmitting channel into the receiving channel. We can measure this to be better than 77 dB, so way better than 1 part in a million. But if you've got relatively high flux in your transmitting channel and you have a handful of photons coming into your receiving channel, that becomes really important. So we had to kill the second channel and just operate in unidirectional operation. But we're able to push out to 250 kilometers of real fiber. And at that point get about 186 bits per second in the asymptotic regime. But I mean, at this kind of range, the finite key analysis is really important. So we get about 67 bits per second doing a finite key analysis, in which case we have to take everything generated from that kind of roughly 2.5-hour block to do that. Stability is very important to us in terms of this actually being practical. So this is operated just over a direct fiber link, so no fiber spools, just 10 dB channel attenuation. But with absolutely no stabilization algorithms, the system could run for about 50 hours straight. That's down to the fact that both of our chips, they have a small footprint of 10 millimeters by 20 millimeters, and they can be mounted on off-the-shelf thermoelectric controllers and stabilized to within a few thousandths of a degree. And if you do that, you basically get phase stability in your chips. And more excitingly for the person actually running the experiments, which is me, I could run the system, power it down, go home, go to sleep, come back in the morning, and then power it back up. And it was always back to where it was before within about 10 seconds in terms of running it. So as long as you keep that temperature stable, and the thermoelectric controllers can do that, then it's an extremely stable system. So in conclusion, we developed an edge-coupled hybrid indium phosphide silicon nitride QKD transceiver PIC, and that allowed us to do bidirectional QKD operation with an actively modulated receiver, which I don't think is actually something we've seen in on-chip QKD either. And the system exhibited features that we found really encouraging for it to be kind of practically implementable. So we kind of take this as we think it underlines the fact that hybrid integration is mature enough now, and it has got to the point where it should be able to be used in quantum technologies such as QKD. So thank you very much. If you're looking for more details, there's as of last week, the manuscript has gone up on the archive. So that's a fantastic place to look for more details. And it should be arriving in MPJ Quantum Information, which has been accepted in principle very soon. So thank you very much for listening. I'm happy to take any questions.
Thank you very much, Joe. Are there questions?
Hi, thanks very much for the talk. So this is a technical question because I don't like free space optical quantum memories. Sorry. So if you go back to your slide where you have the device.
Which one?
That shows the 7.5 dB loss.
Oh yeah.
So there's almost no loss propagating through the device, and your interface loss is only 1 dB. So how do you get to 7.5 dB with that?
Excellent question. In fact, I have another slide that I really wanted to put in, but I just didn't have time to talk about, where I looked at the loss that we have in all 4 chips that we produced. And basically, it's the indium phosphide. So we get relatively low. The fiber to silicon nitride interface, we get about 1.3 dB. The silicon nitride AMSI is only 1 dB, basically. The propagation loss has almost become negligible in this chip. The silicon nitride indium phosphide, obviously, we go through that twice because we go into the indium phosphide, back out into the silicon nitride. So it's contributing 1.8 dB. And then it's dominated largely by the loss of the indium phosphide EOPM. So what we'd be most interested in is actually finding out ways to reduce that loss there.
Can you do a phase shifter straight in the silicon nitride?
So that won't be able to go fast enough. Can we put like phase modulators in the silicon nitride?
Yeah.
No, unfortunately, that platform currently doesn't have that available. Yeah, which is
Okay,
pains we've got
great,
for the
thanks.
hybrid.
Thanks for the nice talk. A simple question. So what is the main reason for the quantum bit error rate rising at higher attenuation? Does it have anything to do with the chip or?
It is, actually, we can kind of see it there, can't we? It's the dark counts becoming significant. So yeah, so once you get fewer actual counts through, your dark counts, which are just 50% errored, basically, become more and more significant. And then your QKD is terminated in terms of attenuation when you've just got too much error from those dark counts.
So, but it's not induced by any scattering or anything of the chip. So
No,
chip
no,
is not the culprit.
No,
Okay.
the chips, that's not anything to do with the chip itself.